कण 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 के की हम देखेंगे, हम लाजिम है कि हम भी देखेंगे, हम 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 देखेंगे। आज बाजार में बाबा चला चलो, आज बाजार में बाबा चला चलो, दस्त अफशा चलो, मस्तो रक्सा चलो, दस्त अफशा चलो, मस्तो रक्सा चलो, आज बाजार में बाबा चला चलो, खाक पर सर चलो, खून बदामा चलो, राह तकता है सब शहर जाना चलो, हाकिम शहर भी मजमाए आम भी, तेरे इल्जाम भी संगे दुश्नाम भी, सुबह ना शाम भी रोजे ना काम भी, तेरे इल्जाम भी संगे दुश्नाम भी, आज बाजार बाबा चला चलो, दस्त अफशा चलो, मस्तो रक्सा चलो, चश्म।
Go for it. Cool. Okay. Someone was going to do an announcement at the beginning, but they're not here, so I'm just going to get going. Okay. You're good. You're released. All right. No boards today. You don't have to manipulate any cameras. Although I do need to manipulate the lights, but I got that one. There we go. Yeah. All right. So, hey, everybody. Welcome back to CS 70 post-midterm. Hopefully you had a good time. I don't have any reflections on the midterm other than, the mean was more in line with, like, I guess, a regular class around here. If you're new to Berkeley, I mean, hopefully you're aware that midterm means tend to be pretty low in the 60s, and that's fine, in my opinion. It basically tells you you don't know everything, and if you got, like, a near perfect score in this class, you're really, really good at this. That's how you should interpret it. So if you have an outmoded mentality from high school or community college where, like, 99 is like, I'm doing pretty good. That's not the case. At Berkeley, a 99 is you're doing incredibly well. We're not as extreme as the Dutch. When I was on sabbatical in the Netherlands, they have a grading system where 6 is passing, and everybody's pretty much okay with a 6. 7 is really good. 8 is extremely good. 9 is for the professor, and 10 is for God, is what they say. So they never give out 9s or 10s for basically anything. So 6 to 8 is kind of the good range there. So here, right, hopefully you didn't feel demoralized, and of course feel free to reach out to us if you were stressing out about the exam or you want tips on how to improve and all that. But a lot of it just comes down to really good deliberate practice sustained over a long period of time. That's basically how you get good at this stuff, in my opinion. I will note that we did have one student complain that since the median was not like 44 like last fall, then there wasn't enough room to really differentiate yourself and get 3 standard deviations above the mean. Sorry, that person. All right. Anyway, okay. I'm not that guy. Okay, so let me tell you about what we're going to do next. we're going to kick off this whole new unit of probability. It's going to be similar in flavor to what I did in the counting lectures. And so I'm just going to give you a sense of the kind of problems we're going to solve. First, I'm going to give you a news article from last year, which was a team of researchers from the University of Hawaii at Manoa who published a study this week that estimated that there was a probability of, they said, 9% in the next 50 years of a magnitude 9 earthquake in the Aleutian Islands, which could be a problem for Hawaii. So it's interesting to think here, what do they mean 9%? Like, we can't live the next 50 years over and over. So what does it mean that it's 9%? And I'll revisit this theme a little later, but that's the kind of question, the kind of things that people say in terms of probability statements. And these are some of the fuzzier ones. There's also some more specific questions, and here I have a question for you, which is I have a couple of different coin flips. So if I flip any coin 20 times, there's many things that can happen. One of them is I get all heads, another is I get that mix of heads and tails. Which outcome do you think is more likely? So I'll let you answer this for a second. I will grab my phone so I can review your thoughts. And do let me know if any of the links aren't working. I think they should all work. Okay. Is it working? Someone get it? Anybody get it? Not working? It did work. You got it. Okay, cool. My phone. Yeah? Are there 21? I mean, maybe. That would be really weird. It's possible. We'll have to double check later. Okay, unfortunately, I can't see what you're answering because my phone refuses to be on the internet. All right, here we go, maybe. Okay, well, I'll look at your answers later, and I'll just tell you what I got. Okay? So it turns out they're both equally likely, and that could be a little counterintuitive because it feels like, well, I mean, the heads thing is crazy. If that happened to me, I'd be screaming. But if the second one happened, I'd be like, all right, whatever. But they are equally likely. They both happen with probability 1 over 2 to the 20th. Assuming there's actually 20. Someone thought maybe there's 21. There might be. It's possible. All right, another question you might have. This is a tricky question we'll be talking about next lecture and the lecture after. So imagine we have 2 shopping centers, okay? Here's one. This one has 3 Indian restaurants. This one has 2 Moroccan restaurants. This other one has only 1 Indian restaurant and 1 Moroccan restaurant. So imagine we pick one of these 2 shopping centers randomly with probability 50%, and then we pick randomly from the restaurants. We could ask kind of a reverse question and say, well, if we ate at a Moroccan restaurant, what's the chance that we pick center 1? We are not equipped to answer this question today, but the answer might not be what you expect. Okay? That's another example of a problem we want to answer. Or, as we'll see, we have many other questions, and today they're going to be kind of toy problems along the lines of like dice and flipping coins. But all of the underlying ideas today are really important for probabilistic reasoning, which then underpins all kinds of really important things that you will do in life, like data analysis or building machine learning models or whatever else. Okay? So in this second half of 70, we're going to give you this really solid foundation for probability, and you will find that probabilistic reasoning is often counterintuitive. There's things you don't expect, like the coin flipping example. And so a firm foundation is what you need to avoid blundering off a cliff and making what are otherwise easy mistakes to make. Now, I will note that this second phase of the class is almost a disjoint class from the first half. This is just how it's always historically been with CS70. We are going to use proofs, okay, so that first couple lectures. We will use counting, which I also gave the lecture for, and I think actually should be part of this part of the class. But then other topics like induction is really not even going to come up, hardly at all. Stable matching graphs, modular arithmetic, error correcting codes, countability, computability, all that stuff is not really going to be used. So you can let that stuff slowly start leaking out of your brain, and then you can bring it back for the final, which will be have these questions but not as many. Okay? So be aware, it's going to be kind of a restart. So if you're getting stressed climbing the mountain up to RSA and thinking about secret sharing, we have new things to think about. So I mentioned counting problems, and ideally in your life right now, like this would all be second nature, and then the rest of the lecture would flow very smoothly, and it would almost feel kind of trivial. But I know you're not there yet, probably. But these are our counting problems from before, which was basically imagining we're drawing k things from a set of cardinality n, and we want to know what are the possibilities. And I'm going to go through these many times today, so we're going to be refreshing them. I also have the 3 I actually care about on the board up here. We're not really going to use counting problem 4 very often, but these are all of our counting problems. So counting problem 1 was I'm taking balls out of a bag, one thing like 2, 5, 7, 8, or whatever. 2 was the same thing except I put the ball back every time. This is also the same thing as rolling dice. And then 3 was the drawing things without replacement and not caring about the order. So this would be like, I have a bunch of cards, you draw 5 of them. That would be counting problem 3. Okay. So I'm not going to talk through all these formulas again. We did a whole lecture on all these. And just be aware, this is something that you really should have down very, very well by the time of the final, that it just feels, this flows right out of your brain. Okay. So let's talk about new stuff. And we'll learn some formal definitions that are going to undergird everything we do for a little while. And I'm going to start with the idea of a random experiment. So a random experiment is we draw k items from a set S with cardinality n. Sounds very familiar from the counting lecture. And an example would be we're rolling 2 4-sided dice. So in this case, we're drawing 2 samples, k equals 2. S is our set of things we're drawing from. It has cardinality 4. And we're going to be drawing, in this case, with replacement. What does that mean in terms of dice rolls? Why is it with replacement? You can get the same number twice. Yes, exactly. A sample point is going to be the outcome of a single such experiment. So for example, 2, 2. So I rolled dice and I got 2 2s like we see here. And then a sample space is going to be the set of all possible outcomes you can get in your experiment. And we'll use capital omega to represent all of the samples that could possibly, all the outcomes that could possibly happen. And in this particular case, the sample space is exactly one of our 4 counting problems from a previous lecture. This is counting problem 2, ordered with replacement. That's how I'm thinking about it. N equals 4, k equals 2. So I rolled a 2, and then I rolled a 2. You can also think about it as counting problem 4, fine, and we'll get to that in a little bit. But for now, I'm going to say counting problem 2 is where it's at. Okay? So there's our sample space. Those are all the things that can happen. This is counting problem 2 tells me these are the 16 things that I can get. All right. A probability space is going to be our new thing. So all this is kind of different words for things we already did. But a probability space is a new idea. It consists of a sample space, same thing we had before. But now we're going to give something extra. It's not just a... We're also going to assign to each of these outcomes a number between 0 and 1 that represents its probability. So we got a function, p, that takes each of these outcomes, little omega. So this is little omega in the Greek alphabet. This is big omega. So you have a bunch of little omegas to make the big omega. And it takes every outcome and it says, hey, 1, 2, you have some probability. 4, 3, you have some probability, and so forth. We have to have probabilities between 0 and 1. The percentage chance, you can think about it, that thing happens if you multiply by 100. And then all the probabilities have to sum to 1. Hopefully this is kind of intuitive from other notions of probability you have walking in the room. In this particular case, the probability distribution, or say the probability function, is just flat. It's just a constant, 1/16. Everything is equally likely. We're rolling 2 fair 4-sided dice. Hopefully you agree if you roll 2 dice, any of the 16 outcomes are equally likely. We could draw a diagram thinking about how this process evolves. First, we roll 1 die, and there's a 1/4 chance that we get 1, 2, 3, or 4. And then there's a 1/4 chance that I get 1, 2, 3, or 4 again. And in all these cases, the probability is uniformly 1/16. There's 16 things that can happen. And one way to think about how these probabilities are composed together is that after rolling this first, let's say, 4, there's now a 1/4 times 1/4 chance that we get 2 4s. Okay? So we can multiply these probabilities together. And there I'm not going to give very much justification other than it matches our intuition. We'll talk about this a little more in a later lecture. But for today, observe that everything is probability, 1/16. Okay? Any questions about this sort of foundational, basic definitional stuff where everything's nice and clean? Okay? Yeah. So the concern was raised that we're double counting the 2, 2 and the 3, 3. And so we'll give an alternate framing in a bit. But if this is the probability, if this is the sample space, if I define it where I consider the order, all of these are equally likely. This is the first die roll. That's the second die roll. Make sense? But there's another framing where you say, oh, well, that's like, I don't want to count 1, 2, and 2, 1 as different ideas. That would be fine, and I'll show you that in just a moment. Before we talk about that alternate possibility of framing, I want to give you an example of a non-uniform probability space. So let's say we roll 2 dice, and they're loaded, meaning that the 1 comes up 5/8 of the time, and all the other numbers come up 1/8 of the time. What will be the probability of rolling 2 1s? Okay, just, I'm just letting you kind of use your intuition here. Oopsie. Okay, I'll double check this thing. Now it's working. Internet, you're bumming me out. There we go. Okay, here we go. Okay, so we're like 83% of you agree, 84%. That the answer is 25/64, and I'll give a nice tree picture in just a moment. So that is indeed the case that if you have loaded dice, the frequency or the chance that you will get 2 1s is 25/64. What about these? So for these right here, how did I get 25/64? I'll show you in a moment. It's just 5/8 squared. The probability of getting these right here will be a 1. So 2 1, the chance of getting this would be 1/8 times 5/8. 1/8 times 5/8, 1/8 times 5/8, 5/8 times 1/8, and so forth. So 5/8 times 1/8 is 5/64. And then all the rest are 1/8 times 1/8, or 1/64. Here's a tree picture, though. Okay, if you were like a little shaky on that, this is why it happens. So when you roll your first die, there's a 5/8 chance you get a 1. There's a 1/8 chance you get a 2, a 1/8 chance you get a 3, and a 1/8 chance you get a 4 for your first roll. Okay? If you roll the 1, what's the chance you get a 1 if you roll, if you already rolled a 1, what's the chance you get a 1 next time? 5/8, okay, so it's also 5/8. And here our probabilities multiply. So we get 25/64. Then we have these other 3 possibilities where we reach 1/8 chances. So 5/8 times 1/8, that gives me 5/64. And then we look at the rest of the tree, and we have, again, these 3 other gold possibilities. Those are the ones which are 1/8 times 5/8. And then we have these 9 green possibilities, which are 2 unlikely rolls in a row, so to speak. And so the fact that we can multiply the probabilities here relies on the fact that these dice rolls are independent. And I'll have a little bit more, again, as I mentioned earlier, in a later lecture. All right, so this right here is a non-uniform probability space because the different outcomes, 1, 1, for example, is far more likely than the outcome 2, 3. Okay. All right. So I'm going to note on notation, I deviate from the notes a little. This was actually an accident last fall, but I decided I liked it because I think it's good to see multiple different pieces of notation so you don't get too fixated on it. So in my lectures, I will use capital regular old P with parentheses. The notes will use a blackboard P and brackets. Brackets is kind of nice because then it's very clear what the P is around. Like, it's a function taking an outcome, and then you have the whole thing in brackets, and then you can use parentheses for other stuff. But I didn't do that, so sorry. But be aware, of course, that notation, it's just placeholders for ideas. They're exactly equivalent, and there's other possibilities than just these. Okay. Another reflection is someone earlier asked, aren't you like double counting 1, 1 in some way, or 2, 1, 1, 2? It seems there's like a weird, I'm just uncomfortable with the notion that some of the draws involve repeats and some of them don't. So we could go to counting problem 4. I don't have it on the board for reasons that'll become clear in a moment, but we could also do unordered with replacement where we say those aren't the possibilities. Like, 1, 2 and 2, 1 aren't really different. So let's just call it 1, 2. That'll be my canonical representation for that outcome. Okay, great. And so now I have just these outcomes. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 of those. That is also just the size of the number of different, counting problem 4. So you can think of it as you have a string of length 5 that's binary, and you have 3 separators, or equivalently you have 2 non-separators. And so you end up with 10 total items that are possible, or outcomes that are possible. But the downside of this, one reason I don't like this, is that even if the dice are fair, what happens over here with the underlying probability? If we have a probability space for fair dice, what happens to the probabilities here? Are some of these more common than others? I mean, it sounds like probably yes, because I was asking the question. Yeah, like 1, 2, for example. There'll be 2 different ways of getting this 1, 2, right? So if we're ignoring order, if we say 1, 2, and 2, 1 are the same thing, and we just like use this single symbol, 1, 2, like a 1 and a 2, in that case, this outcome is going to have probability at an eighth, because you could either get it by rolling a 1 then a 2, or a 2 then a 1. And it just makes reasoning about whatever you're trying to do with your probability problem just harder. So in general, whenever we have a choice between framing as counting problem 2 or counting problem 4, counting problem 2 is the way to go. We will almost never use counting problem 4 in the probability part of the class. It is a nice counting problem, the stars and bars problem it's sometimes called, or the multi-set counting problem, but it just doesn't lend itself naturally to the kind of probabilistic reasoning that we do. So we use CP2 because it gives us a uniform probability space. This is a subtle point, but I think a good one. In other words, if we want to get a uniform probability space, that is, I want all the probabilities to be the same, and we'll see why that's useful shortly, then we will prefer CP2 over CP4. We have a choice. It's our choice. We're mathematicians. We can decide these are the outcomes. We can decide these are the outcomes. Either is perfectly fine, but if you pick this one, then you're going to end up with probabilities that are all equal, and therefore you don't have to actually think about different cases. Okay? Now what's interesting is that probably we don't care about the order of the dice at all when we're trying to solve problems with dice. But pretending we do makes the calculations easier. So we're playing like Catan, the game, and I want to know when I roll 2 dice, what's the chance I get a 6? I care about the sum, but it might be easier to reason about the problem if I pretend I care about the order. And what I mean by pretend I care about the order, it's if I define my sample space so that we distinguish 1, 2 from 2, 1, and so forth. We consider the order when enumerating the possibilities. Okay? Small point, subtle point, but you'll notice when you read the notes, they don't really talk about this choice. They just use CP2 without saying why, but this is why they use CP2 instead of CP4. Okay? All right. One more piece of definition, which is events, and this is going to set us up for what we're going to do for a while. Okay, so an event is a very natural and important notion in probability. It is simply a subset of our sample space. So I have big omega, which has 16 things in it. It's a set of 16 things, and I'm going to define often events I'll give by the letter A, sometimes with the subscript to make it clear. And so an example of an event would be, I don't know, AF1. That's our first roll as a 1. Okay, what samples belong to this event? 1, 1, 1, 2, 1, 3, 1, 4. Now, I should note, for this question, you really need to use CP2 in order to, I mean, you don't have to, I guess, but it's much more natural to do CP2. But we could also say, like, the sum of the dice is not prime. Okay, so what outcomes are in there? Okay, what about 1 plus 1? That's 2. Is 2 prime? Yeah, great. How about 2 plus 1? That's fine. Ooh, but these ones, those are not prime, because 4 is not prime. Also, what about 4 plus 1, 3 plus 2? 5's prime. I like the prime guy. These are prime. Anything I'm missing? Or not prime? 4 and 4. That's 8. Okay, so this event is weird, right? It's these specific 7 samples, and I defined it intentionally to be weird. It's just these 7 outcomes. In this particular case, I guess it doesn't really matter if you defined it using order or not order. But again, reasoning about it, if we want a uniform probability space, I recommend CP2 instead of CP4. All right, so events could be anything, and a lot of what we're going to do for the next couple weeks is going to be finding the probability of events. That's the whole rest of today. So what is the probability of an event? It's very natural, again, this definition. It's the sum. So the probability of an event, is the sum of the probability of the individual samples in the event. Okay, so I just take every sample in the event, 1, 1, 1, 2, 1, 3, 1, 4, and I add up their probabilities. I don't know why it's not italicized in bold, so it goes. And so the probability of this event is just going to be the sums of these 4 different probabilities. For fair dice, what's that going to be? What's the probability that our first roll is 1? I heard a sound. 1/4, right? So it's 1/16 plus 1/16 plus 1/16 plus 1/16, or 4/16, which is 1/4. Okay, you can see it visually. This is a quarter of the weight of the sample space, you could think. Like 1/4 of the samples belong to this event. Or you could just sum up the individual probabilities. Okay. If we have unfair dice, the one we had before where 1 appears 5/8 at the time, now it's going to be 25/64 plus 5/64 plus 5/64 plus 5/64. Okay? In this case, it ends up being 62.5%. All right? Yeah? Why would you want loaded dice? So you can cheat at Dungeons and Dragons. That's my answer. Okay. Question for you. Let's suppose, actually, no, the less glib answer is these type of basic models are used as models for the real world. So you might imagine that this is something about, you're trying to like model user behavior or like server load on a computer, and you just say, okay, there's like 9 things that can happen and they each have different weighted probabilities. So it's a very natural model where I might do that like trying to model course registration, like 70 is this much popular versus data 8, and then I can run simulations. All right. So question for you, if we're using the loaded dice, or 1 appears 5/8 at the time, what is the probability of the event that the second roll is greater than the first? This is a new experimental style of question. Let me know what you think. Okay, this will give you a little. And I hope these questions are engaging and not a lot of work. I like to keep you awake. Okay, we got 1 answer so far. And it wasn't me. And you can chat if you want. Oopsie. Sorry. Okay, hopefully you all had a chance to at least think about the problem, even if you have not answered it. So this is a 2-step process. The first is to figure out which samples belong to a second grader. So among these 16 things that can happen, how many of them have a second roll which is greater than the first? 6. And where are they? 1, 2, 1, 3, 1, 4, 2, 3, 2, 4. Yeah, it's this corner. Everything above the diagonal. Okay, so I can highlight the event. That's the event. And then what is its probability? Well, we just add the probabilities of the outcomes in this event. So these all have probability 5/64. And these all have probability 1/64. And so we just multiply it out, we get 9/32. Okay? That's your first event. That's non-trivial. Okay? But there's lots more. And they get really rich. I mean, this one is sort of I can do it by inspection and look at it, but we're going to have some interesting sort of tricks we can play. It's a lot of this recognizing, oh, it's one of these counting problems. And I think these problems can be really fun. Also, make me feel, at least when I was an undergrad, dumb. But now that I've gotten good at it, it feels obvious to me, which is a great feeling. And maybe you will get there too by the end of the semester. Maybe you're already there if you're a math Olympiad guy or gal. All right. Okay, so let's see some examples of counting events that are a little more interesting than this one. Any questions about this, though, before I continue? This is the foundation. If you get this, great. You can leave the lecture feeling like you've got the foundation you need to do stuff later. Okay? All right, so let's see another example. I'm going to flip some coins. I'm going to flip 16 times some coins. So question, what is the sample space? Like, what is big omega? How big is it? And what's the probability of any specific outcome? So somebody want to give me a sense of what the size, how many different possibilities there are? Yeah? 2 to the 16th, right? Yeah. So this is just counting problem 2 again. In this particular case, it's n equals 2. There's 2 choices. The cardinality of the set I'm drawing from is heads, tails. And we're drawing 16 samples. Here are all of them. I only listed 2 explicitly, and I think there's actually 16 in each of these little strings. And here the total size is 2 to the 16th. So what's the chance of any specific outcome? 1 over 2 to the 16th. They're all equal. So all the probabilities, if I listed them out, they're all 2 to the 16th, 1 over 2 to the 16th. Next question. Let's say A sub 6H is the event where we have exactly 6 heads. What's the probability there? Think about it for a second. I'm going to hide behind the podium while you think. There's no yell key thing for this one. Try and predict where I'm going to go. And if you're watching the video, you better pause and think about it. Okay, let me walk you through it. Okay, so the probability of A6 heads is going to be the sum of all of the different things that have exactly 6 heads. So all you need to know is how many different samples have 6 heads. You can't list them all, but you can figure out how many there are. So how do I do that? Well, that's actually just counting problem 3, right? So I have 16 different places the heads can go, and I pick 6 positions. All right, so this is just counting problem 3. The size of this event is 16 choose 6 or 8008. This is the kind of gymnastics that you want to be able to do without thinking. You're not there probably yet, but by the end of probability, you really want to get to that level where it's like, yeah, okay, cool. This is 16 choose 6, okay? So then the probability, it's just 16 choose 6 times 1 over 2 to the 16th, because each one has weight 2 to the 16th, 1 over 2 to the 16th, so we get around 12.2%. Now you can impress your family or whoever. And then you can prove it to them by flipping a coin 16 times, hundreds of thousands of times, and see, look, it works. Okay. There's something I always wanted to do when teaching Data 100. Maybe I should have done it in this class, where I just get everybody to record themselves flipping a coin 10 times. And then there's a pretty good chance that one of you gets all heads, and then you can be like that person. Anyway, some other day. Maybe if I teach Data 8 someday. All right. I should note you could also have written it 16 choose 10, because in the counting problem 3, it doesn't matter, separators, it doesn't really matter, sorry, this isn't choose. I think I said separators, there's no separators here. But I can also, of course, always choose the other way around. That's the nature of the choose function, okay? Another way to think about this, other than just I'm adding up 8,008 of these things, is to say the following, that if I have, what do I want to say here? So we can also think of this probability as the fraction of the outcomes that belong to this event. In other words, the total event size is 2 to the 16th. That's the number of different things. And there's 8,008 that belong to this event, so this will be 12.2%. And in general, this is true for a uniform probability space. When I said earlier you want to pick CP2 and not CP4, it's because you're able to use this right here. You can think about the probability of an event as simply the ratio of the cardinality of the event to the cardinality of the whole space. You just figure out what fraction of the space this is in this event. Okay? Yeah?
What is the equivalent formula for the situation where we have a loaded die or something?
We'll do the loaded dice, and just that's the next example.
Or we have like a cheat coin.
Yeah, if we have a loaded die or a cheat coin, that's exactly our next example. Okay? But if everything's fair and you have a uniform probability space, every sample has the same weight. You're just counting the size of A versus the size of omega. Okay? And this is a common technique for probability problems, especially in our class. You're just computing the relative size of two sets, and there's our formulas for counting the size of two sets. Okay? So you think about this. Big omega is counting problem 2, where you have two choices. You're drawing 16. There's 2 to the 16th possibilities. Over here, you have counting problem 3. I have 16 heads, and I'm choosing the position of 6 of them. So it's just 8008 over this number. Okay? All right. Your question was, what if the dice or the coins are unfair? What do we do then? So if your probability space is non-uniform, we can't use this little rule right here. This formula doesn't work. We have to actually weight our samples. We'll just use the basic formula we had before. We have to actually sum the individual probabilities, which vary on the overall probability space. Okay. So let's suppose we have now an unfair coin. And this is, again, to your question earlier, why do I care about this? This is a very common model in engineering where I say, I think my hard drives in my data center will fail with a maybe 1 out of 10,000 rate per day, or whatever it might be. So you can think about, if you're modeling how often you need to replace your hard drives in your data center, you can think, once you know that failure rate, and you have some sense of how much uptime you want, or like how much maintenance, like how often you have to send somebody in to replace drives, then you can run simulations again. And then you can say, okay, based on my model about flipping coins, this is how often I need to go replace the drives. So we'll use an example here where our coin has a chance of heads of 1/3 and tails of 2/3. And let's suppose we're doing 4 flips in a row. So I'll do a couple examples. What's the chance that we get 4 heads, and what's the chance that we get head, tail, head, tail? Okay, and I'm still, again, using CP2. I'm considering order. Okay, so what are these going to be? Well, the probability of getting 4 heads is going to be 1/3 to the 4th power. And you can think about it as a tree diagram, which I have very small here. Thank you, LLM, for making this for me. This is dot, by the way, which is a nice visualization tool. And my prompt was, make a dot diagram for me. So if I got 1/3 chance, 1/3 chance, 1/3 chance, 1/3 chance, that's when I get 4 heads. Now, the LLM didn't quite nail it. That's not how I would have labeled that box, but it's very small, so that's okay. So that's 1/3 to the 4th. And then head, tail is 1/3 squared times 2/3 squared. So that's, I took a 1/3, 2/3, 1/3, 2/3. Okay? So this is a non-uniform probability space. These two different outcomes have different probabilities. Okay? That's doing good. All right. So chance that I'd like you to compute an event is, what's the chance that we have exactly 2 heads? Okay. Keep the blood flowing. I'll give you a hint in a moment. I'll sit in my question chair. Okay, so there's 2 things you need to know. You need to know the chance of getting any particular outcome that has 2 heads, and then you have to know how many of those outcomes there are. That's my big hint. Can I wait just a tiny bit longer? Okay, so what's the chance we have 2 heads is how I would do it. I would first note there are 6 of these, exactly, where there's 2 heads. Do all of these have the same probability as each other? All of the circled ones do. Not every sample has the same probability, but all of the circled ones do. And what's that chance? It's 1/3 squared times 2/3 squared. So that's the probability of any specific 2 heads outcome. They're all 4/81st chances. So there's 1 unit of probability across all of this, and each of these gets 4/81st of it. Okay. Which one of these has the highest probability? All tails. This one has the most, and as you move your way this way, you get less probability. So these ones have a medium-ish amount. Okay. All right. So each one of those has 4/81st, and then what do we do with those? We add them. So we add these probabilities, and how many of these are they? 6, and what are they? They're all equal to this number, so the answer is just 6 times 4/81st. You could also say it's 4 choose 2 if you like. That's fine, but that's the visual version. Okay? Any questions about this? Yeah, so it's a 2-step process of identifying probability of any specific outcome, and then how many? Yeah. Well, that's a good point. I probably should have said exactly here. So I will, if I could write, I would. Here we go. Pen. Exactly. Otherwise, it's more complicated. But we have that coming soon. There you go. Look at that good handwriting. I don't know what that is. Pilgrim hat. And then this guy's smoking a blunt. I don't know why I did that. I was a middle school student one time. That's why. All right. I don't know. That was really stupid. But I don't even smoke weed in the year 2025. All right. Suppose that our experiment consists of 16 flips. What is the chance that we have exactly 6 heads? What do you think? How would I do this one? What will be the texture of solving this problem? Yeah? Yeah, 2/3 of the 6 times 1/3 of the 10. That's exactly right. So we got that. And I'm going to have another question. So that's key. First thing I do is I realize that all of these outcomes have this exact probability. What is the probability of A6H if we have here Z? This one I'm only going to give you 1 minute. This is a speed less than that. 40-second speed round. If each of these individual outcomes has probability Z, what's the probability of having exactly 6 heads in terms of Z? I think this is a straight-up free response, too, so. Okay. Come on, phone. Okay. I can't even see your answers, so. I just realized this lecture is going to go on Billy. I might get banned. I don't put them on there, but someone inevitably posts all my lectures on Billy, the Chinese YouTube. So, hi, Chinese viewers. I don't know if the word blunt got appropriately translated or if I got dubbed. Because everything's auto-dubbed now, too. All right. I feel embarrassed. But sometimes you just got to go for it. All right. I promise little time, but I still want to see what you're saying. Number of ways to choose 6. Okay, I surrender. Okay, I don't know what you said, but the goal is we had to add up all these. So how many of them are there? There are 16 choose 6, or equivalently 16 choose 10. That's fine too. Okay? So the overall probability you have exactly 6 heads is 19% because each individual possible outcome is this probability, Z, and then we have 16, choose 6 of those, okay? If you got this, you're in pretty good shape. If not, you will practice after lecture. Okay? Yeah. 16, choose 6 over 81. 16 to the power of. Oh, 16 choose 6 n minus. It would be n factorial over n minus k factorial times k factorial. Yeah. I'll keep going. All right. So if we think about this visually, before on a non-uniform probability space, you cannot do this. You can't just say 8008 over 2 to the 16. That doesn't work. Instead, you need to actually weight each of the possibilities by the appropriate amount, right? Whatever it might be, okay? So here, you can't just say it's 8008 over 2 to the 16th because every point in this entire big omega space doesn't have the same probability. So instead, you need to weight, you use the general formula where you're adding up the probabilities of each individual outcome. We know that each of the outcomes in A6H has the probability 1/3 to the 6th times 2/3 to the 10th. And how many of those points are there? There's this many. That's the cardinality of A6H, the cardinality of the event, 8008, okay? So we can't just divide the 8008 by 2 to the 16th. We need to take into account the weight of the individual samples, okay? There's one slightly more complicated version of this we can do, which is imagine we want to count the number of outcomes with fewer than 4 heads. So this is back to your point earlier, like exactly versus not exactly. So how many different ways are there to get fewer than 4 heads? We could have what? 0 heads, 1 heads, 2 heads, or 3 heads, okay? So what is the chance of any single outcome that has 0 heads? It's going to be 1/3 to the 0 times 2/3 to the 16th. And how many ways are there to get 0 heads? 1, right? There's 1 of them. It's the all tails, okay? Chance of any specific outcome with 1 head is going to be 1/3 to the 1 times 2/3 to the 15th. And there are 16 of those. Okay, what happens next? There's some chance of getting 2 heads. And how many of those are there? 16 choose 2. So here's my table where I can put the probabilities of each. So the chance of getting any specific outcome that has 3 heads is 1/3 to the 3rd times 2/3 to the 13th. And there's 560 of those. So if we wanted to know the probability of this event, we're just going to compute, I guess I'll call it the sum product of these two things here. So it's going to be this right here. There's 1 of those. There's 16 that have this probability, 120 that have this probability, 560 that have that probability. And visually, you can think about it as follows. There's just 1 of those in that event, which we have 0 heads, and it has some probability, which we said earlier is 1/3 to the 0 times 2/3 to the 16. Then there's A1H, which is bigger, it's 16. Then we got 120, I think it was. And then we had 520, or yeah, I think that's right. So each of those sets is a little bigger as you go up in the number of heads, and the probability shifts as you go. So we're thinking just about how much weight this contributes. It's going to be 120 times this probability. And we just add up that. Each of these products of the sizes with the weights of the individual points in these events, these separate little events, okay? So the probability of having less than 4 heads is the probability of having 0 plus 1 plus 2 plus 3, okay? Any questions about this? Yeah? What's here? What? These?
Are we going to be using those for something else? Do they mean anything?
Yeah, I mean, this one's 120. They mean something for sure. They tell you the number of different ways to get that many heads. Yeah, very important, yeah.
If we have like 450 heads or less, are we like just left to calculate this manually, or is there some kind of way to put it together?
Is there a nice closed form solution to combine many of them? That's an interesting question. I don't know, but yeah, I'll think about it, yeah. If you're a Math Olympiad person, let me know after. You might already know the answer. I don't know it. I'll note you can also think of this in terms of unions. So we can think of the event of less than 4 heads as the union of these different subsets. So it's a bunch of different points. You just form their union. And then we say the probability of this event, which is the union of these 4 events, is just the sum of the individual probabilities. Well, think about this more carefully. This is not in general true. The probability of unions of events isn't necessarily the probability of the overlap. So for example, imagine I have an event like, I don't know, you have less than 5 heads and you have an even number of heads. Okay? Like those are the 2 events. So what's the probability of less than 5 heads or even heads? You couldn't add those 2 probabilities together as 2 separate events. Why? Just like intuitively? There's some overlap. So what do you think you do to fix it? Inclusion, exclusion. So we'll do that later, but not in this lecture. Okay. All right. All right. Let's talk about poker hands. So this right here, if you get this is the essence of this lecture. After this, it is just sort of math tricks, and they're not even that deep. But this is the most important thing. You must understand this, and if you walk away from this, you'll be able to get through the discussion and a lot of the homework without too much trouble. These are the basic moves. Everything else is kind of like, this is the basic set of objects you can manipulate on the chessboard, and then after this, it's going to be like, I don't know, like tactics, and not so much fundamentals of how the whole thing works. Okay? All right. So talk about poker hands. This is a slightly different framing of problem than anything we've seen before, but the same principles apply. Interestingly, by the way, if you look at the slides online, there's shading in the PowerPoint on my Mac, but not online. I don't know why, but this was the thing that made formatting between my Windows computer and my Mac super annoying, so curses again to Microsoft. I beg you to make a good Google, I want you to go work for Google Slides, and I want you to add an equation editor, okay? This is the most important job that you can do for me and your life. Thank you in advance. Anyway, in the meantime, though, so in the standard deck of American playing cards, you have these ranks and these suits. Other countries, you have other playing cards, but that's what we have here. We have ace, 2, 3, 4, and so forth, and it doesn't really matter what these cards mean, but the point is that there's these different ranks, so it's like the number of things on the card or whose face is on it, and then we have these suits. Does it have this symbol, this symbol, this symbol, or this symbol? There's 13 times 4, or 52 total cards. When you shuffle them, we know that if you have 52 things and you permute them, there's 52 factorial permutations. And what that means is that if you shuffle a deck, no 2 shuffled decks have ever been the same. I did have ChatGPT look at my slides to make sure I didn't have any typographical errors, and it said, don't say that. It's too firm. It's like, I don't know. I'm going to say it anyway. I don't think it's ever happened, so take that large language model. I don't think it's ever happened that 2 people have shuffled a deck randomly and they got the same one. Very, very unlikely. What can you do with these cards? Well, you could play a game. For example, poker. The old school version of poker, someone gives you 5 cards, and maybe you got an ace of hearts and a 2 of clubs, and play spades. 2 spades, 5 spades, king spades, queen of diamonds. And we could say, okay, well, if we're framing this as another one of these counting problems, what's the deal? So what is the cardinality? If we think of this as a random experiment, what is in the cardinality of the set we're drawing from? What's K? What is the size of the sample space? Which counting problem is this? Kind of redundant with, is this with or without replacement or order? And is there uniform? Is the probability space uniform? So I don't know. Give me N. Who thinks, what's N? 52. Okay, what's K? 5. Which counting problem is this? 3, sure. Or? Nope. 1. You could do a 3 or 1. So 3 would be if you don't care about the order. So if you were to take your hand of cards and move them around in your hand, if you consider those 2 different hands, then it's counting problem 1. If it's the same, it's counting problem 3. I'm going to do counting problem 3. So as I said, it's counting problem 3. That's drawing without replacement and ignoring order. What's the cardinality of this space? Okay, so that's going to be 52 choose 5, because you have 52 cards and you're drawing 5 of them. That's 2,598,960, a number you may know if you're a poker head, I guess, maybe. And the space is a uniform probability space. Okay? We can also use CP1, though. I'll show you in a minute. Okay, which of these 2 hands is more likely, do you think? There's this one, which is pretty good, and this one, which is less good. What do you think? Which one's more likely? I'm hearing some equal, so yeah, right. They are equally likely. It's a uniform probability space. Okay? What about the probability of certain things that can happen in poker? There's a thing called a flush, and here I'm including the straight flush, so that's still a type of flush, and that is all hearts. So you get 5 cards. What's the chance that you get all 5 of the same type? And for you, I'm just going to say, what's the number of different? What's the event where we have a flush of hearts? This is not ace of hearts. This is the event where you have all hearts. Okay. I don't know if I explained that well. So your question you have to answer is, how many different heart flushes are there? Ignoring order. Here's all the hearts. Okay. Back in the question chair. Oh, that appeared. I used NordVPN to watch Dutch TV. Can we wait for a couple more? I know free response is less fun. Okay, so the number of different heart flushes. You have 13 of these cards. So how many different ways are there to get a heart flush if you have 13 hearts? Well, you said it on the thing. It's 13, choose 5. That's just counting problem 3. Or, yeah, you have 13 items and you want to pick 5 of them. And that's the number of different ways to form a heart flush. Okay? So that means out of 13 hearts, there's 5 different ways to get, there's 1,287 ways to get 5 hearts. How many different symbols are there? There's 4. So how many total different flushes do you think there are? 4 times that. So there's 5,148 different ways to make a flush. So if you were to sit down and try and enumerate them, like 2 of hearts, 3 of hearts, 4 hearts, 5 of hearts, 6 of hearts, 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, 7 of hearts, and so forth, then you would get 5,148 of them. Okay? So the chance of getting a flush is just the ratio of the total number of possible hands as the denominator and the number of flushes as the numerator. Okay, so we're just counting the relative size of 2 sets, yes?
So does this prove that does this like basically prove that getting a flush, that betting a whole lot of money on getting a flush?
Yeah, if you have a flush, then it's a good thing to run with, yes, indeed. You could also do this in terms of counting problem 1. I'm going to speed run this just to show you the math is basically the same. The only difference is that if I frame it as counting problem 1 where I consider order, then the size of the number of hands is 311,875,200. Where did that come from? It's just counting problem 1, so we're multiplying these numbers together, 52 through 48. Why are there more hands? Because you're counting each of the k factorial permutations as different hands. So you're getting 120 times as many different hands because you're considering each of the 120 permutations as distinct. It's still a uniform probability space. If I want to count the number of heart flushes, it's the same thing, except now it's counting problem 1, 13, 5. So there's 154,440 heart flushes. Same number as before, but times 5 factorial. Why 5 factorial? Because that's the number of permutations of 5 cards. There's that many flushes. There's that same probability. Okay. So you could do it either way. So I have a quick observation, which is that both counting problem 1 and counting problem 3 worked, which is interesting in terms of a bit of asymmetry. Earlier when we were rolling dice, I said you should choose counting problem 2 instead of counting problem 4. But when you're drawing without replacement, it doesn't actually matter if you consider order. Why is this? Well, when we are doing dice rolls, if we ignore order, that means that samples with repeat draws are, even if it's fair, they're less likely than draws that have different ways to get there. So for example, for 2 dice rolls, the chance in CP4 of getting 1, 1 is less than 2, 1, even if it's fair. But when you're drawing without replacement, that's not a concern. You can't get repeat draws in a single sample. That just can't happen because just by definition, there's no replacement. This is only a very subtle little point. This is probably too much for you in this lecture, but I had to say it, and probably I should add it to the notes because it's not in there anywhere. Okay. So in drawing without replacement, the basic idea is it doesn't really matter if we pick counting problem 1 or 3. Both of them give uniform probability spaces. I tend to pick 3 because all you're doing if you pick counting problem 1 is you're just making your life harder by a factor of k factorial. Like basically you add an extra factor of k factorial to the numerator and denominator. Why bother? Okay. By contrast with rolling dice, there isn't that nice k to 1 function that makes the 2 problems equivalent. But it is the case with counting problem 1 and 3. Okay, this is a little bit beyond the scope of the day, but wanted to mention. Okay, let's talk about balls and bends. This one's pretty quick. So let's say we have 20 balls and we throw it in 10 bends. Ready? I threw one. I threw another. They keep landing places. It's amazing. Here we go. Where are they going to go? Okay. And how do I know when to stop? I know when to stop because the last ball is gold in color, and those are all the balls landed. So I could repeat this many times, and I might have questions like, how likely is it that one of the bends is totally empty or whatever else? And this could be used for modeling, for example, hash tables, if you've taken 61B or 47B or community college data structures class, because items land in fairly random places. So let's say we wanted to answer questions like, what's the probability that bin 1 is empty? How do you think we should define the sample space? And how do we ensure that our probability space is uniform? Which counting problem do you think makes sense here? Does this feel like, I guess first question, does this feel like a problem with replacement or without replacement? Heard some withouts? I'm hearing more withouts. That's interesting. Yeah? I think it's with. Why do I feel like it's with replacement? Because like the bins get reused, okay? So one way to frame this problem is with replacement. If I am doing it with replacement, just like based on kind of pattern matching what I was saying earlier, if I had to choose between the 2 counting problems that are with replacement, which one should I choose? CP2 or CP4? 2. 4 is not even on the board, right? Because it yields a non-uniform probability space. So I'm going to treat it just like 20 ordered dice throws. It is exactly the same as 20 ordered dice throws, right? I mean, you insert something into a hash table. The first one landed in bin 5, then 6, then 2, and so forth. And the rolls can be between 1 and 10. So I'm one indexed here. Okay. Now I should note that if I choose CP2 as our framing, I've effectively labeled the balls. I said that the very first ball landed here, the second ball landed there. And that's true even though the original problem, as I framed it, had no labels. But if I label them, it's going to make the probability space uniform. Again, this is a very subtle point that's very elusive when you're first learning this stuff. But by choosing CP2, we're effectively labeling the balls, even if the question we're answering doesn't care about the labels at all. Okay, so the question I had was, what's the probability the first bin is empty? I'm going to label the balls to make that reasoning more concrete, okay, more uniform in terms of the probability space. Okay. So then what is the probability that the first bin has no ball, that it's empty? Well then, since all the outcomes are equally likely, we just need to count the number of outcomes where no ball lands in bin 1. Just that same thing. I have all the space of everything that can happen. And how many different things can happen? There's 10 to the 20th. And why 10 to the 20th? Because you pick one of 10 bins, then you pick another of 10 bins, and you repeat that 20 times with replacement. Okay, so how many of them have no ball in bin 1? Well, this is kind of like the flush question. It's the number of ways that 20 balls could be occupying the other 9 bins. Okay? So the event A will be the first bin is empty, and 2 through 10 have something in them. Okay, so question for you, how many such ways are there? What is the size of the event A where there are no balls in the first bin? Nope. Nope. Okay, is this question showing up? You guys like these multiple choice ones. I'm getting lots more answers. Okay, I'll give you my answer. So this is none other than our old same exact counting problem. It's just that now, instead of having 10 choices, I only have 9. So I had 10 to the 20th choices when there was total flexibility. Now I only have 9. Now, if you didn't get that problem, again, you're not at the point where this stuff's going to be supernatural. But I do recommend that tomorrow you look back at it and you maybe go back to the slide looking like this and you try and think, well, what is the answer? I think it's a good thing. Or argue with your friends about it. Okay? You can think about this as assuming the first bin is empty, how many different configurations are there of the other 9 bins? Okay? So then what's the probability that the first bin is empty? Well, we know there's 10 to the 20th possible configurations in all of omega, the big bubble. And we know there's 9 to the 20th in the little one, the purple one from earlier, in this case, the gold one. So there's a 12% chance that the first bin is empty. Other way of putting it is if you inserted 20 items into a hash table that had 10 different buckets, there's a 12% chance that the first bin would remain empty. Okay? All right. And I'm not going to, well, I don't know. Maybe I could take a question. Maybe. I think mostly it's just getting in the reps, though, to get good at it. How about the other way? What's the probability that bin 1 is not empty? What do you think? Yeah? 1 minus that. Yeah, 1 minus. So that's a common trick. The probability of the complement of an event is just 1 minus, so that's 88%. And in general, for an event, the probability of A is going to be 1 minus the probability of not A, where not A is the complement. If we were to generalize this beyond 20 balls going into 10 bins, we could do it symbolically, and we could say if we have k equals m and n equals n, where k is the number of draws, then we just generalize the same pattern. You'll see this in the notes. It's the same thing you'll see in the notes. They're just picking a specific, or I picked a specific n, 10, but they have the generic version there, and you find that the probability that the first bin is empty is n minus 1 to the m over n to the m, which is cute. Okay. You can also rephrase this a little bit. You can just divide out the n, and you get 1 minus 1 over n to the m. And you'll see this formula, again, in the notes, and this is why. So this is the intuitive version. Hopefully it flows naturally. And again, why would you care about this? It could be, for example, modeling jobs sent to servers, modeling how many items go into what hash table bins, though I don't know why that's useful. The top one, though, I can imagine being actually useful. I got one more of these counting problems for you. You guys feel like we're getting a lot of exercise today. I feel like we're on some kind of marathon here. But I hope you're feeling good about it. Okay. All right. Let's say we have 50 people in a room. We have many more in here. You might have seen this before, maybe. Says the question, what's the chance that 2 people among 50 share a birthday? And we're going to ignore leap year birthdays. Anybody here a leap year birthday? Yes? You are ignored. Sorry. My daughter was this close, 6 hours from being a leap year baby. And I curse her for being late every day. It's a little bit. It's a sweet curse, because it would have been cool. So goes. Anyway, what's your gut feeling? Who thinks the chance of 2 people in a room of 50 sharing the same birthday is less than 20%? Just intuitively, okay? Like maybe 50%? Yeah, 90%? Okay. So we got a spread, and we have a lot of I don't knows. Okay. Okay, let's think about it in terms of counting problems. Great. So if we're imagining drawing birthdays, ignoring you, what is the probability space here? What's the cardinality of the set? 365, right? There's 365 birthdays. Again, sorry. How many are we drawing? 50. Are we drawing with or without replacement? With, because we're picking birthdays. Are we considering order? Nope, don't really care. What's the cardinality of the sample space? Well, it depends on those other choices. Oh, wait, I said no, but I picked yes. Why did I do that? Because I wanted a uniform probability space. Okay. All right. So no would have been a fine answer. It just would have made the calculations harder. So I chose yes because it gives us a uniform probability space. CP2 better than CP4. Even I got tricked today by myself. What's the cardinality? Because it is counting problem 2, it's 365 to the 50th. Okay? And if you get this down, you might try and redo it in terms of counting problem 4, and you'll think, this is annoying. I should have just considered order. Okay? So again, this is just counting problem 2 again. This is balls and bins with 50 balls and 365 bins, or rolling a 365-sided die 50 times. All the same problem. Okay? So the overall big space, the big omega, that one's 365 to the 50th. And I want to know what's the probability that 2 or more people have the same birthday. So I'll call A the event where 2 people have the same birthday. I will give you some examples of such samples. One of them is 1, 1, and more stuff. Or 5, 5, 5, or these where there's 2 66s. The trouble is, it's really hard to figure out the cardinality of A from this. Okay, so we have to be a little more clever, and this is probably the most like, God, I wish I could do a backflip. That would be cool. It'd be like the most gymnasticsy move of the day. Didn't gain that skill in my life, so it goes. So what we're going to do is something very clever. Okay. So as is sometimes the case, the complement is easier to compute. So if A is the event where at least 2 people share a birthday, what is A bar? It's the event where no one shares a birthday. Okay, so for example, 55, 1, 67, 2, 99, and there's no repeats. That would be an example. So all we got to do is figure out what the size of that space is, and then we'll be in shape. And those of you who are really good at math can already see where it's going, and everyone else, let's figure it out, okay? So how many samples are there with no repeats? What is that? It's something we've seen before. It's actually just a slightly different counting problem than the one we're doing. We're doing CP2. What is this? It's something. Well, we're going to force that there's no repeat birthdays. So we just recast the problem as, okay, no repeat birthdays. So that could be CP1 or CP3. I guess either one kind of makes sense, we said earlier. I'm going to say without replacement here. And what did I want to say? Oh, yeah, what's the cardinality? That's what I want you to think about. Right. Okay, so this, I think, is my second to last such question. Okay. Oh, that's the right question. Sample size. Sample set size. Oopsie. I'm going to write a hint over here. Maybe that's on YouTube. If not, I just wrote on the board Omega considers order. Okay, cardinality of the sample space. We're actually going to use CP1 here because the earlier framing we considered order. And if we want to be fair and actually be comparing like to like we need to compare, or the omega considers order. So A and A bar should also consider order. Maybe something worth, if you don't believe me there, after class, just sit down and write down a small universe in which there's only like 2 people and there's only 8 different birthdays, and this will become clear. Okay? So this sample space then is just going to be 365 times 364 all the way down to 316. Okay? So this right here, the size of the sample space is given by CP1. This is given by CP2. So the birthday paradox, in a nutshell, is basically the ratio of the size of the set generated by CP1 to the size generated by CP2. But then we have to do 1 minus. Because remember, the thing we actually care about is do people share birthdays, not do they not share birthdays. Okay? So if you just plug in these numbers that we had before, 365 to the 50th down here, and 365 times 364 all the way down to 316, you get this expression here. Okay, what does that number work out to? It works out to, we'll use Wolfram alpha, okay, if we're real lazy. Okay, so this thing right here is 3%. Okay, in other words, the probability that we, CP8 or 2 or more of the birthdays is the same. Oh, he's right. That's just this quantity. Okay, right. So this number right here, this is the chance of what? That they do, no idea, someone said. This is the chance that 2 people do not share a birthday. So that is the ratio. That's 3%. And so that means that this overall number here is going to be 97%. So in other words, if you get 50 people together in a room, there's a 97% chance that they share birthdays. So I whipped through that pretty fast, admittedly. There's a recording of me you can watch again. But fundamentally it boils down to, it's the ratio of the cardinality of the set for CP1 to the ratio of the cardinality of the set for CP2. But only using the word ratio once. Okay. All right? We could generalize this and say, well, what if it's n people? Well, in that case, what we're going to end up with is the event where 2 people do not share a birthday is given by this. This is the size. That's the number of different configurations. And then we'll just divide by 365 to the n, and we end up with this expression. I will note that it might be a little messy to actually evaluate this expression directly, so we could try and be a little more clever, but I will note that if you were to plug this thing into Java, for example, you'd get overflow. Python will work fine. But a question you might think about later is, there's other ways you can be more clever with computation, but I don't really want to talk about it. But if the idea of like, how do I actually compute this ratio without just sticking it in Wolfram alpha is interesting to you, I'm happy to talk about it at office hours. Okay. Okay, I feel like I went a little too fast, but so it goes. What you end up with here, in the end though, is that if this is your number of people, and you follow the same procedure for different numbers of people, you will find that the probability that 2 people share a birthday in a room hits about 50% at 23. So if you only have 23 people in the room, you can feel pretty good that 2 people share a birthday. By the time you get to 50, there's a 97% chance. If you have 60 people, it's 99.4%. And this is just evaluating that equation that was really big at various different. So I want to reflect on these different problems we did. If we flip coins, we roll dice, we toss balls and bends, we pick birthdays, those are all counting problem 2, right? We're just picking some different cardinalities. These problems are all fundamentally the same. Other approach, and one example of why this is useful, as we just saw, like one of the things that comes out of this, we do the birthday paradox calculation, is that if you want to know the chance you get the same die rolls in 23 rolls, or sorry, if you get the same die roll in 23 rolls of a 365-sided die, you get 50%. That is the sense in which these are all the same problem. By contrast, drawing cards, or picking the position of heads, or picking birthdays without repeats, those are all counting problems 3 or 1. Okay? So there you go. Okay, I'm going to give a little summary, and then I'm going to give just a tiny little problem that you guys have mostly already seen based on last semester. Okay. So I want to know that probability is hard, and even a guy at the end of a lecture who knows this material pretty well can make a stupid mistake about the pigeonhole principle. Your intuitions can be wildly wrong, and rigor is really important to be correct. In all of these cases, basically what we did today is we are counting different sizes of sets and sometimes weighting them. And I'm not going to enumerate all those things. Okay, so the very last thing I want to mention is the Monty Hall problem, which is really a next lecture topic, but I do want to introduce it at least in these 2 minutes. Okay. So you guys might have seen this game before, where you have 3 doors, and you can win a car. 1 door has a car behind it, and 2 doors have a goat behind it. Okay? Now you want a car, right? Who wants a goat? Okay, that's respectable. Who wants a car? Okay, about 50-50. Well, I'm going to assume that the car is your goal. Okay? So the rules of this game, and this is where we're going to wrap up. So you pick a door, then the host always shows you what's behind the other door, one of the other doors, and the answer is always a goat, and you always get a chance to switch doors after the host shows you the goat. So let's do a couple rounds, and then that'll be the end of our day. Okay, I picked this door, and it says switch or stay. Which one should I do? You want me to switch? Oh, you lose. You got goat. Okay. I picked this door. Should we switch or stay? Switch. We won. Okay, should we switch or stay? Switch. Oh, we lose. Switch or stay? Switch. We win. Okay, switch or stay? Switch. Oh, you lose. Okay. So I encourage you, if you want, you could play this game before next lecture, and we'll pick up from there. I hope that was